All right. So, I know this is a long way out, but some of you helped me out, like in the fall, we did that over at, what school were we at? Anyway, so Mays Elementary, I've actually done that years ago. And unlike Craig Woodman, who's a bunch of cheapskates, Mays Elementary is actually going to give us pizza. So if that's, it's going to be the same type of deal. I'm not for certain, but it's probably going to be about that same type of format where we do science for the kids, and there you go. So just kind of put that on the radar. I don't need a decision today, but if that kind of works with your schedule and you need some service hours and like exciting kids about science, that could be a cool deal. Okay. So some of you are asking about different speeds and different mediums. So on page 474 of your book, okay, there is a chart that lists the different speeds of sound in different mediums. Okay? So when in doubt, Nathan Nelson, use your book as a resource. Okay?
I use Google. My bad.
Don't.
I went back and I used the book because
Yeah, because that's what everything is based off of. So especially, and this is even relevant to today's lecture. So if this page in particular, chart in particular, has some different things that are relevant. So like there's going to be table 15.2, which gives different animals what frequency they can hear in. And then this is going to be especially important today. When you get to page 486, there's a chart of what we call decibels, which is like how intense the sound is. So today, on today's assignment, they're going to ask you about some questions about decibels and how you use that information. So they're listed on page 486. Okay. So with that said, popcorn, which one did you want me to talk about?
4.
Problem 4 or question 4?
Problem 4.
Okay. So visualize this. So you've got this length of metal 4 meters long. Okay, and that's a decent length. Okay, so if you consider like this is 1 meter, this is a long piece of metal. So microphone on the other end picks up 2 pulses of sound, one that travels through the metal, one that travels through the air. The pulses are separated in time by. So let's start with this. You have 11.0 ms. You have to know what that means. What does the ms stand for? Milliseconds. Okay? So if you don't know that, then you're just kind of dead in the water. So imagine this, like here's this hammer, okay? So you're going to have 2 sources of sound. One, the sound is going to travel through the metal itself, and then the other one is going to travel through air. Okay? That's what you've got, right? That's what you've got. So on this one, and because of the, yes, you seem perplexed.
Do you have that white soap thing?
That what?
That white soap thing?
hand sanitizer.
Yeah, hand sanitizer.
Oh dear.
I thought you said white cellophane.
Nah, I don't know what it is. And smoke acetic acid.
It's white.
You got me. It's like a milkshake. Can I use it as a milkshake? Thank you.
All right. So here's the story. So you know on this one that what you're trying to figure out is the speed of sound in air, or excuse me, the speed of sound in metal. So you also know that distance equals velocity times time. So you know the distance that it has to travel in air. You know the speed of sound in air, what? Go. Is 343 meters per second. So you can figure out how long it took for that sound to travel in air, which should be longer. So you got that time. And so you're going to get this time. So what's important is that 11 milliseconds, the pulses are separated in time by 11 milliseconds. So it doesn't make any difference what the time is, it's separated by 11. So you can figure out how long it takes to travel in the air. And now you need to carry a lot of digits out. So what you're going to do is you're going to take that 4 meters and divide that by 343 meters per second. You're going to carry out a lot of digits. That's going to be like 0.0 something, okay? Carry out some digits. So once you get that time, then you can subtract how much the difference was in the times, okay? So then that's going to tell you, oh, that's how long it took for the sound to travel through the metal. Then once you get that number, then you can work backwards and figure out the velocity of the sound in the air, because you know velocity is going to be distance traveled divided by time. So that answer on number 4, this is an ish, especially depending on this one, like how you round it. But that time or that velocity should be in the high 5,000s. Okay?
Or low 6,000. Low 6,000.
What?
If you carry out full values, 6,040.
Huh?
If you carry out all the full values, like you keep your calculator values, it's 6,040.
Yeah. So that's why I said the high 5. This one especially gets wonky depending on how you round it. When you get to number 6, okay? So if you ever have like an ultrasound, sometimes you use that like look at kidneys and things like that, and it's pretty cool. And they also actually use the same process on oceans to map out like the bottom of the ocean. So you send a signal out, it has to hit something, and what's important is that thing has to bounce back, okay? So you're told that the image is 12 centimeters. 12 centimeters is about like yay, okay? This is a huge difference. So it's got to travel 0.12 meters down, hit the surface, and then bounce back up. Okay, so this has to hit and bounce back up. So what's the total distance that it's going to travel? 0.24 meters. Now, you can go through and find that chart. You can find the velocity of the sound in human tissue. And it's like 1,000, it's around 1,500. Okay? So then you can take that 24 meters and divide that by the velocity in sound, because that's what it's got to do. It's got to hit and bounce back. Then you can figure out how much time that takes, which isn't going to be very long. Okay? It's going to be a pretty short amount of time. Then you can get that period, which is going to be that time, but it asks for how many pulses per second. So again, it's the same idea. What you found was period, so then you take the inverse of that, boom, there's your frequency, and your frequency on that one should be around 6,000. Okay? And again, that's pulses per second. Okay? That's a lot. All right? If you think about generating 6,000 pulses per second, much faster than that.
You're like close.
That was about 2. Okay? That was 2. All right? Oh, speaking of problem number 2, that answer to problem number 2 should be around 100.
Wait, which one?
Oh,
problem. You got it right. I was looking at a question number 2. I was thinking question
So number two.
I messed it up before. I got something around 60,000.
Oh shoot, I messed it up. Okay,
Oh
so
my God.
Hey, I never would have done that.
this way.
Actually, I just use your paper as the answer.
That's what our temperature is.
I did that just to see.
I just like the crap.
I really did. Okay, anything else on the assignment? Going once, going twice. Problem 3? Much less than 1 second. Like 0.0 something.
0.07. Oh,
You're good, man.
What did you do?
You make it sound like I don't know the odd answers are in the back of the book.
Because it's
I love how
12 centimeters, I get
it's
double
like
since
some
it
hidden
goes
secret.
down.
Doesn't know the odd answers in the back of the book. What an idiot. It's like, I picked the book.
It's the opposite of running back to the I cannot. That's how, Michael. That's how. Ryan, you only find your time. 0 in front of the decimal point.
How do you learn English labs that
What does that
were
equal?
stuff that I did?
That's 1 over seconds.
I know it, but like, I need to double
That's
check
6.
to make sure I did this.
That's what I did. I don't.
Okay, we're good. Once, twice, sold. Fantastic.
How'd you do the 1.56? Because that's time. Because this is, I got frequent minimum time between time, which is basically. So time between pulses would be the inverse of this? Yeah. I figured it out.
Yeah, that's what covered it by for so long. I just ended up like,
Did you get 1.56 times 10 to the negative 4? And that would be seconds. Yeah. And then what is like this?
maybe, I think, why did they do the
6, 4.
all I ever know?
You take it. Oh. It just depends on how we round it. Okay, I didn't really round. I didn't round either, so. Let's see. 1, 4, 2. Okay. 2, that's close.
Oh, you want to talk about being a fish?
Yeah. Well, you only found one answer, but it's reaching your ear directly and then going past your ear, reflecting from the back. But that's how much time does it do between
Okay,
those
Mara, we still going?
two? Yeah, we never stopped.
Okay, so here's the next thing that we need to look at. And this is a situation or an equation that basically you dealt with a lot, you just don't know that you have. Okay? So this is kind of going to go old school in terms of some old school units. So you have this simple equation, which is power, is equal to intensity multiplied by area. Okay? So intensity is W per meter squared. Anybody have to know, remember what W might stand for? Watts. Units. Watts. Okay? You got watts, right? And watts is the same as joules per second. Okay? And this is going to be multiplied by area. Okay? Now, typically, functionally, how you use this is intensity is power divided by area. So this is why you have intensity in watts per square meter. So you don't know it, but you have used this equation every time you use your garage door open. Okay, and you're going, Yeah, that has nothing to do with the garage door. It's everything to do with the garage door. So here's the story. Imagine that you have a single candle in a darkened room. Okay, so imagine that I darken the room, and I put a single candle right in the middle of the room. Okay? When you're right beside it, what are you going to feel in terms of heat? Warmth, right? If you're right beside it, that's going to feel really, really warm, right? Now, as you move away from it, what's going to happen? It's going to decrease. So it's going to decrease as you increase the distance. There's an inverse relationship, right, between density and radius, okay, or intensity and radius. So, if you're right here beside that candle, that's going to feel really warm. The farther out you go, the less warmth you're going to feel. Even if you look at this in terms of in the intensity of the light. So if you stare at a flashlight and it's really close to your eye, that's not good, okay? But if it's far away, then it appears much brighter, or much less bright, much dimmer. And we do the same thing actually with stars. So when you look at the night sky, you see that light as a function of the intensity of that light. But that light is being spread out over a large area. You look at our sun. Our sun looks really bright. Why?
It's so close to us.
It's relatively close to us. Okay? If you're out, if you live on Jupiter or Saturn or Neptune, our star is going to appear as this tiny little dot. It's not going to look that much different than the other stars in the night sky. So it looks really bright, which is a good thing for us, because we're at a distance. So the distance that we are from the sun is actually what's known as the Goldilocks zone. If we were much closer, probably about 10% closer, we would be so warm that the oceans probably would all evaporate off and we wouldn't have water. If we were about 10% further away, we'd be so cold that all the water would freeze and we'd be an icy planet. So we are in the sweet spot. We're warm enough to have liquid water, but we're not so warm that all the water evaporates. We're far enough away to have liquid water, but we're not so far away that all the water freezes. Okay? So this is why we're what we call in the Goldilocks zone. Okay? We're just the right distance away from the star. Now, when you're talking about how you calculate this area and how this all works in terms of units. So remember, power is work divided by time. Okay? Old school, power is work divided by time. But power, remember, is also some change in energy. Okay? Doesn't matter what that energy is. Could be us, could be whatever it is, some type of energy. So if we do a little bit of rearranging and we look at energy, okay, we can rewrite this as energy is power times time. Well, power has units of what? Joules per second. So if I multiply joules per second by seconds, I get joules. There you go. Now, how you calculate area? There's two different ways that you can calculate area in this equation. So if you're talking about your eardrum, okay? So your eardrum, you can treat that as like a circle, and that would be pi r squared. So in some of the problems you're going to have on the assignment today is going to talk about, hey, what's the intensity of sound that strikes your eardrum? Okay, that's just going to be pi r squared. So I wish Louise was here because we could talk about decibels and hearing loss. Okay, so this is why if you have your AirPods or your headphones, momentary loss on that one, you don't want to crank that up. And here's the reason why. Because intensity is power divided by that area. So in this situation, if you're really, really close to that sound source, that's going to be a really intense sound, okay? Striking your eardrum. So you're going to have this really intense area very, very close to you. Now, the other way that you can talk about this area, and it could be the sun, it could be a candle, it could be a flashlight, it doesn't make any difference. So the other way you can look at this is if you treat this as like a point source, and imagine that that light is spreading out like in a sphere, is spreading out in the sphere. So with that one, what you want to do is that area is 4 pi r squared. Okay? So this is if you have one source and it's like spreading out in a plane wave. So here's the deal. So if you look at that area, and if you have a really, really, really small radius from that point source, okay, that's going to be a small area, which means if you look at this in terms of intensity, and intensity is power divided by that area. This is the distance that area is a function of how close you are to that source. So the power is a fixed value based upon how loud you have it, okay? You can adjust that. So if this is a really small area, and because that's squared, that area is basically, if you think about that energy spreading out, that's going to be the intensity that's going to hit like on a given amount of area. So if you're really close to that sound, that's going to be a really high intensity. Now, this is where this equation plays into your garage door opener. Okay? Like, how does this work with the garage door opener? Well, you press the button on your garage door opener, okay, if you have a proximity key or anything like that. If you go out to the parking lot and you live at 21st and Mays and you hit the garage door opener, it's not going to work. Why?
Too far away.
Here's the reason why. The top part of that equation, the power emitted by the garage door opener, that's the fixed value. You're not going to change that number. Okay? What you're changing is the 4 pi r squared. Okay? So when you get, and this is true, this is literally why they call it a proximity key. So if you have a proximity key on your car or a garage door opener on your house, it's the same idea, then what's happening in this equation, as you get closer and closer and closer to your house, that wave energy, right, is getting more and more intense per unit of area because you're closer. So this is why there's a threshold distance that your garage door opener won't work, because there's a threshold of intensity that has to be met. And if you don't cross that threshold of intensity, then it doesn't work. Okay, and the same thing with the proximity key in your car. So there's a certain intensity threshold. If you're too far away from your car, you can't open up the door. Okay, so if you leave your key, yes?
I thought P was power.
It is power. That is absolute power.
So what's proximity?
So the power is a fixed amount of radiation that's being emitted from your key or your garage door opener. That's a fixed value. You can't change the top number. But what you alter is the area side of it on the bottom side. Okay? So when you're closer, you're dividing by you're dividing by a smaller area, and that increases that intensity. Okay? Does that make sense?
Yeah.
Okay. All right. Now, a lot of times what you want to do is compare different intensities based upon different distances. So this will make sense in just a second. So I have I1 over I2 I put those 4 pi squared. Okay. So a lot of times what you want to do is compare intensities at different locations. So if you look at this as a ratio of two different intensities based upon location. So all I did was substitute how you calculate intensity for each one. So this is the power of the source, that's a fixed value, divided by 4 pi r1 squared, 4 pi r2 squared. So this is going to be the different densities, okay? Distances away. So what's going to happen to the power from the source? That's going to cancel out, as are the 4 pi. So this R2 is in the denominator of the denominator. So what you end up with is I1 over I2 equals R2 squared over R1 squared. Now, let's look at this in terms of how this would play out.
How did that move up?
This is like the.
Because
denominator.
your R2 is in the denominator of the denominator.
Yeah,
Oh, okay, got it. Yeah.
So it would flip up to the top. Got it? Okay.
Got it.
Okay. So here's what you've got. So let's say that you have some source of sound, it's a speaker, it's a light, it doesn't make any something that's emitted in waves. And you can measure that intensity when you're 1 meter away, which will only be about like yay. You measure that sound intensity, and that's 10 watts per square meter. Okay, so you know that number. And then you want to figure out what's going to be that new intensity at 4 meters. So when you do this, clearly, when you find I2, should it be bigger or smaller than 10? Smaller, why?
Because you use.
Yeah, you're further away, okay? So like if you all can hear me talking now, if you go to the back of the room, it's harder to hear me. Why? That energy is getting more spread out. The energy is still there, but it's just more spread out, okay? So I want to find, so what I would do, because I hate fractions,
Right.
I would go I1 times R1 squared equals I2 times R2 squared, right? So I want to solve for I2, so that's going to be I1 times R1 squared over R2 squared. So you've got 10 watts per square meter. Don't forget to square these, so R1 is divided by 4 meters squared, and what do you get?
Oh, you don't like fractions.
0.625 watts per square meter. Okay? So we quadrupled the distance, right? So that intensity dropped like a rock. Now the same thing, and you'll see this is somewhat how very relevant to if you look at how solar energy works. So here's the sun, we're out here on the earth, right? So if you could build them, beyond just the environmental issues, solar panels would work much better at Mercury or Venus. Why?
Closer to the sun.
Yeah, they have much more intense light. So even if you look at Mars, solar panels on Mars don't work as well. Why?
Further away.
Yeah, that if you look at this as a function of r squared, so Mars being further out receives much less sunlight per square meter. So to generate the same amount of electricity from solar panels on Mars, you would have to have much bigger arrays because they don't get as much sunlight. So the same thing, actually, this becomes a deciding factor when you look at space probes. So the Cassini mission orbited the rings of Saturn, okay? So Saturn's relatively way out there. So because Saturn was so far away from the sun, it wasn't practical to have solar panels to generate electricity, okay? You could on Mars, like the Mars rovers, those have solar panels. They're great until a dust storm hits and they get covered with dust. They don't work and then you lose power with it. Connection. Small detail. But if you're way out here at Saturn trying to orbit those rings, solar panels won't do you any good because of the fact that you are so far away from it. So then you have to, they actually use basically like a nuclear battery to generate the electricity to keep that thing going. Okay.
Mr. Birkin,
What?
Mars doesn't have an atmosphere, so how's there dust storms?
Oh, no, it does have a small amount
Oh,
of
but it's
that.
so big. All right.
I mean, appreciably no,
Okay.
but it does have it.
Okay.
Okay, it's like 1% of ours, something like that. It's a very
Wait,
small
does
percent.
Mars have a magnetic field?
For the week.
No, that's DB. I'm sorry.
No, decimeter. Yes, decimeter. So your joke doesn't even make sense. You said decimeter. This is flip stuff. My jokes, yeah, white piece happen. Oh, that's so. You ever seen the station for this? Oh, my bad. Oh, you ever seen the station? Oh, my bad. Hey, Mary.
I know he did.
I've never seen this first. That's just all I know. I feel like you're
Okay, so you just need to know how to use this equation. Don't memorize it. So what this does, this gives you sound intensity as a logarithmic function of intensity. So on page 486, table 15.3, Nathan Nelson, listen to this.
Yep.
Okay, there's a chart. And what it has is the intensity of sound measured in watts per square meter. So this equation, your I naught, okay, that's your absolute lowest limit that human beings can hear. So this is 1.0 times 10 to the negative 12. That's a fixed value. Okay, so your I naught is just a number. So what this tells you is, yes, huh? What does what stand for?
The big B.
Oh, this is just your sound intensity. This is decibels, and it's just a logarithmic function. So this just tells you the intensity of the sound that you're going to hear at that
And
point.
the dB is the decimal.
Yeah, so this is, because it's a log base 10, that's why you're multiplying it by 10. Okay? So if you want to figure out, okay, like for example, if you look at this, they write it as a fancy B, but it's also technically measured in decibels. It gets a little bit wonky when you look at the units. So here's the point of this. This I naught is a fixed value. So, and that's the threshold of hearing. So if you put that, if I equals I naught, so in other words, if you're just at that threshold of hearing, if you put 1.0 times 10 to the negative 12 over 1.0 times 10 to the negative 12, you're taking the log of what? 1. What's the log of 1? 0. So that in decibels is going to be 0. Okay? So if you look on this chart, like classroom, normal conversation at 1 meter. Okay? So that has an intensity of 1.0 times 10 to the negative 6. So if you come in here and you take 1.0